When we don't have equations of the form y equals f of x, so y equals some function in x, whatever that might be, we are hitting a problem because we don't currently know how to solve those sorts of equations. Luckily, there's a technique called implicit differentiation, which you know about because you clicked on this video, which helps us solve this problem. So what we're going to do to implicitly differentiate is essentially pretend like the y's aren't really there, and then what we'll do is we'll adjust. So I'm going to continue to do what I've always done, which is differentiate every part of my function with respect to x. So this is what we have always done with our differentiation questions. We've said, okay, then let's take all of the x values and we will differentiate those functions. And I'm going to do that exact same thing, except that I'm also going to do that to anything in terms of y. Now, some of these terms, the ones that are in x, so this x squared term, the 3x cubed, and also the 3, which should have a d by dx on around it, can be differentiated normally. Those are absolutely fine. So we're left with currently 2x from our x squared differentiated. This d by dx, which just means differentiate with respect to x, 5y to the 4. We've got 9x squared from our 3x cubed differentiated. This differentiate with respect to x to y, which again we don't know anything about yet, but we will figure some stuff out. And then our 3, when it differentiates, goes to 0. Okay, so what is happening with this 5y to the 4 term and this 2y term? Well, for 5y to the 4, what I'd really like to do is differentiate this thing according to y. So if I had d by dy of 5y to the 4, that would be fine, because that would be 20y cubed. It's like if I'd had a or r or l in my equation, whatever the variable is, if we're differentiating with respect to that variable, we know how it behaves. That's absolutely fine. But the issue is I don't have d by dy, I have d by dx. So I've got to somehow link those two. Now, taking our d by dy and effectively multiplying it to dy by dx, now we know it isn't really a multiplication, but it's a connected rate of change, and thus it behaves that way, we could see that our dy's sort of cancel each other out. We're changing with the same rate respective to those. And we're left with d by dx, which is the thing we were being asked to differentiate with respect to. So it seems like if I really want to differentiate with respect to y, that's okay, as long as I include this term, this dy by dx. Well, that's fine, we can do that, we can just write that down. So d by dx of 5y to the 4, the original thing we were being asked to differentiate is, well, let's pretend that the the x that we're trying to differentiate by is actually a y, and differentiate that and get 20y cubed, and then chuck dy by dx on it. So going back to our original equation then, we can differentiate this perfectly well using implicit differentiation. So my first term differentiates just like normal, that would go to 2x. My second term, we're differentiating with respect to x, we don't want to be doing that because it's a y function, so we'll differentiate with respect to y, which would be 20y cubed, and because we've changed the variable we're differentiating by, we will pop a dy by dx on that term. We continue through as we did before. We've got our 9x squared, differentiating that 3x cubed term. I've got another term in y now, so we'll differentiate that as if it were we were being asked to differentiate in y, and that would be to minus 2, but I've got to remember to put that dy by dx on it because I've changed the variable. The 3 goes to 0 still. And now I have an expression in terms of x, y and dy by dx. Now I was asked to find the derivative, dy by dx. So I should now just rearrange this equation so that I get dy by dx equals, and the expression will have x's and y's in it, and that's fine. So, moving all of the terms with dy by dx onto one side, so that's my 20y cubed dy by dx, and also now plus 2 dy by dx, moving that over and the sign changing, and then I can move all the terms without a dy by dx onto the side, so that's 9x squared and minus 2x. Now I'm going to factorise out my dy by dx from the terms on my left hand side. That gives me 20y cubed plus 2, and I've still got the right hand side. You could factorise if you so chose, and then lastly I can divide to give me dy by dx, which is 9x squared minus 2x, all divided by 20y cubed plus 2. In this second example then, I've got something similar. I've got an equation in both x and y. So I'm going to have to use implicit differentiation to find the derivative. The difference with this example is that I have a product here between x and y. So I've got 7x squared y. Now, it's a product. I've got the function x squared multiplied to the function y and scaled by 7. Since it's a product, to differentiate this, I'm going to need to use the product rule and implicit differentiation. So we're going to combine those two techniques. Okay, I'm going to attach the 7 to the x squared term, so that'll be 7x squared, and that is multiplied to y. So setting that up using the product rule notation, I've got u equals 7x squared, v equals y. If I differentiate those two terms, then du by dx would be 14x, and dv by dx, because that's what I'm doing, differentiating with respect to x, well, if I pretended that y was an x, it would differentiate to 1. And then I have to remember that since I've changed the variable, I need to multiply by a dy by dx. Applying the product rule then, u times dv dx plus v times du dx, I end up with 7x squared times by 1 lot of dy by dx, so just dy by dx, plus 14xy. So that's my left hand side. The first term of my right hand side, my 3x squared, goes to 6x, and my second term, well, I'd like to pretend that it was differentiating with respect to y, which would give me 12y squared, but since I've changed my variable, I need to remember to put a dy by dx on it. And that's it, implicit differentiation.